Exercise 2, time in flight. Time in flight can be obtained easily using the y component and the displacement equation, noting that delta y is 0. The displacement equation is delta x equals v naught t plus 1/2 at squared. For our purposes, we will be using the y component. 0 equals v naught sine theta t minus 1/2 gt squared. One of the t's will drop out and we'll get negative v naught equals negative 1/2 gt squared. Multiplying through by negative 2g on both sides, we get 2v naught sine theta over g equals t. In this situation, range is simply delta x. Recall that the only acceleration on the object is in the y direction. Therefore, v sub x, the x component of velocity, remains constant during the object's trajectory. We will be using the displacement equation and the x component. So delta x equals v naught cosine t plus 0. There is no acceleration in this direction. We will be using the value obtained for total time in flight for t. Position and velocity at some time t. To solve for position, use the displacement equation and the value for t that you are given. Position will have an x and a y component. You will solve for them separately. Recall that the acceleration in the x direction is 0. And in the y direction, it is gravity and points straight down. To solve for velocity at some time t, use the velocity equation and solve for the vertical and horizontal components of velocity. The horizontal component of velocity is constant along the object's trajectory. The vertical velocity, however, has an acceleration of negative g. You will find the final overall velocity by using the Pythagorean theorem, where Vf equals the square root of each of the final x component and the final y component squared. To find the landing angle, theta final, you will use the inverse tangent function, and you will use v final y divided by v final x.